We have defined the electric potential energy of a charge to be the quantity of potential energy the charge has relative to another electric charge. As we move a charge from one point to another, the electric potential energy of the charge will change. This is what is referred to as the electric potential difference, or the voltage difference. Remember that only differences in potential are physically meaningful. So only the difference in potential between 2 points is measurable, and you've probably heard this referred to as voltage. So let's relate this back to our electric field. Remember an electric field defined as the electric force exerted on some electric charge. We also discovered that moving the charge through the electric field will result in some change in the electric potential energy of the charge. So moving our charge from point A to point B by some electric force causes a change in electric potential energy that is equal to the negative of the work done by the electric force. Now we just defined the electric potential difference as the change in electric potential energy per unit of charge when it moves from one point to another within a uniform electric field. We can write an expression for this voltage across the points as just that. So the electric potential difference, or the voltage difference between 2 points, is equal to the change in electric potential energy between those 2 points divided by the magnitude of the charge that is moving. Since the change in potential energy is also equal to the negative work, we can substitute that in as well. Of course, we can also replace the negative work with a negative QED as well. Notice our Q above and below, so they will cancel out, leaving us with the voltage between point A and point B to be equal to the negative of the magnitude of the electric field times the distance between point A and B. When we look to label this unit, we find that it works out to be Newton meter per coulomb, or a joule per coulomb. This is given a special designation called the volt. Now I want to reiterate here that when we talk about voltage, we are talking about a change in electric potential between 2 points. You cannot have an electric potential measured at some point without comparing it to another electric potential somewhere else. So what is the maximum voltage between 2 parallel conducting plates separated by 2.5 centimeters of dry air if air will support a maximum electric field strength of 3.0 times 10 to the 6th volt per meters? Well, this is pretty straightforward in that we know the electric field and we know the distance. So finding the voltage is just a matter of plugging those into the equation. Of course, we are going to double check our units and make sure they all match up, and we find 7.5 times 10 to the 4th volts. So suppose an electron gun has parallel plates separated by 4 centimeters and gives electrons 25 kilovolts of energy. What is the electric field strength between the plates? We are given the distance and the voltage, so it is a pretty simple matter to find the electric field strength. So if we have 25 kilovolts, the potential difference is 25,000 volts, separated by 4 centimeters, and we end up with 6.25 times 10 to the 5th volts per meter. So then what force would this field exert on a piece of plastic with a 0.5 microcoulomb charge that gets between the plates? Well, we decided that the force of an electron field is the charge times the strength of the electric field, so that seems pretty simple. Remember that micro means 1 millionth, or 10 to the negative 6th, and we have a force of 0.313 volt coulombs per meter being exerted on our plastic. If you're looking at that label and wondering what in the world that means, remember that 1 volt per meter is equal to 1 newton per coulomb. And if we move those labels around, we get an expression for 1 newton, and therefore can write our answer as 0.313 newtons. Now, an electric field, whether it is uniform or not, will point in the direction of decreasing potential. In this setup, we again have our parallel plates, one that is positively charged and one that is negatively charged. The positive plate is defined to have a high electric potential, while the negative plate is defined to have a low electric potential. The difference in charges of the 2 plates is actually what creates the electric potential between them because they are separated by some distance. The force on a positive charge is always in the direction of the electric field, and in the direction of the lower potential. So if Q is positive, it will be pushed away from the positively charged plate on the left because like charges repel. So a positive charge will always move from a high voltage to a low voltage. The force on a negative charge is always opposite the direction of the electric field and in the direction of the higher potential. This is because opposite charges attract and the negative charge will be pulled towards the positively charged plate. Another way to think of electric potential difference is to consider the amount of energy that is gained by a charge in a given situation. For example, our positive charge, when released in the electric field, will begin to move. It moves because a voltage difference exists between the two plates. In doing so, the charge gains kinetic energy. The same thing happens with our negative charge when placed near the negative plate. Because there exists an electric potential difference, a voltage difference, between the two plates, the charge will gain kinetic energy as it moves through the difference. So suppose you have a 12-volt motorcycle battery that can move 5,000 coulombs of charge and a 12-volt car battery that can move 60,000 coulombs of charge. How much energy does each deliver? Well, a 12-volt battery means it has a potential difference of 12 volts across its terminals. So when charge moves from one terminal to the other, it's just like moving our charges between the charged plates. And the charge moves through a potential difference of 12 volts. The energy delivered by the battery comes from the change in the potential energy of the charges moving inside the battery. So if we solve for the change in potential energy, we know how much energy is being released by the battery. The change in potential energy of that charge is equal to the 12-volt potential difference times the magnitude of the charge. The charge on the motorcycle battery is 5,000 coulombs, so the change in potential energy is 6 times 10 to the 4th joules. The car battery holds a charge of 60,000 coulombs and so has a change in potential energy of 7.2 times 10 to the 5th joules. So even if you have two batteries with the same potential difference or voltage, they may not be able to supply the same amount of energy. Also note that when figuring the change in potential energy, we determine the absolute values. Since the battery is losing energy in the process, to be technical, we would want to say that the change in potential energy is negative, meaning that the potential energy of the battery is decreased. So what if we want to know how many electrons pass through a 30-watt headlight each second if run by a 12-volt battery? Well, we are looking for charges moving through the headlight in 1 second. According to our equation, in order to find the charge, we need a change in potential energy and a change in potential difference. Potential difference was given at 12 volts, and we also know the power of the headlight. Remember, power is joules per second, so we actually do know the amount of energy flowing through the light. So every second, there's a change in potential energy of negative 30 joules. Once we know that, we can find the magnitude of the charge moving through the light as 2.5 coulombs. However, we are asked about the number of charges. If you remember from our discussion of static electricity, the charge on one electron is 1.6 times 10 to the negative 19th coulombs. Taking our total charge per second and dividing it by the charge of one electron, we find that there are 1.56 times 10 to the 19th electrons flowing through the headlight each second. We can also calculate the final speed of a free electron accelerated from rest through a potential difference of 100 volts. Taking our expression for conservation of energy, we can substitute in what we know. The electron starts at rest, and we are going to convert all of its potential energy into kinetic. Initial potential energy is going to be the charge times the voltage, and kinetic energy is figured for an electron in the same way it is for any object. So we can solve for v squared and plug in what we know. This gives us the velocity of the electron at 5.93 times 10 to the 6th meters per second. Now earlier we discussed how the gravitational field does not have much of an effect on electrons. The fact that an electron can be going this fast helps support that claim. So we have defined the electric potential energy of a charge to be the quantity of potential energy the charge has relative to another electric charge. As we move a charge from one point to another, the electric potential energy of the charge will change. This is what is referred to as the electric potential difference, or the voltage difference. This voltage difference is calculated by taking the change in potential energy and dividing it by the magnitude of the charge. The resulting amount of energy per charge is labeled as a volt.